Numerical modeling of transportation cost minimization in surface mining. Abstract: this study aims to minimize ore transportation cost in surface mining by numerical modeling. Minimization of ore transportation cost is very important in case of multiple locations of ore deposits such as phosphate ore of Aljalamid. In Saudi Arabia, the ore is found in 3 locations. The present numerical model aims to determine the best position of processing plant. The suggested mathematical based on the factors such as number of main locations, reserves in each location, transportation costs in different locations, and transportation distance from each ore deposit location to required processing plant position. Computer programming was used to solve the considered mathematical model. The main results of the study are determination of processing plant location, contour map of additional cost in the area around the optimum location, and the presented model is very useful in similar deposits. Keywords: numerical modeling, simulation, transportation cost, cost minimization, optimum processing plant position. 1. Introduction. Cost of transportation represents one of the main items of mining projects. The factors affecting the cost of transportation in mining are transportation distance, or tonnage, and transportation method. Many transportation models were suggested such as Larwood and Benson Model 1, Anderson Model 2, Bechtel Model 3, and Zimmerman Model 4. These models tried to minimize the cost transportation 5 to 10. Fjellstrom 11 presented a model to estimate the transportation cost of ore to crusher and waste to backfilling rooms in Renström mine. Wagoner 12 presented many contributions for development of transportation models. Brazil ETAL 13 suggested a model to optimize the transportation costs of underground mining roads. This model focused on the underground mine networks. 2 models were investigated by Dharma and Ahmed 14. These models presented for application in 2 iron ore mines. These models were applied to optimize transportation cost. The numerical results were agreed with real-world situation. Shepard 15 suggested a transportation model based on transported quantity, distance, shipment delay, transport technology, and route. Mahran ETAL 16 suggested 2 mathematical models to obtain the optimum location of the processing plant in Bahariya iron ore mines. These models based on ore reserves and transportation distance, but it did not take into consideration the transportation costs of different locations in El Gadida, Gurbi, Nasser, and El Hara iron ore deposits. Also, the gravity center calculations are not accurate due to uniformity or thickness assumption and method of calculation. Inwood and Key 17 investigated relationship between trade costs and trade volumes by using modern different tools such as evidence on effective transport costs of iron ore trade. Linear programming was used by 19 to minimize cost of transportation in mining. Chen ETAL 20 proposed a model based on classical transportation problem and transport path. Ahmed ETAL 21 presented a study to minimize cost of transportation by linear programming problem. Joshi 22 suggested a method to decrease cost of transportation. The method based on linear programming and was solved by using 4 different methods. Ahmed 23 presented a method that named Best Candidates Method, BCM, to solve optimization cases. The objective of his method to find optimal solution. Novikov ETAL 24 considered an integer model to minimize cost of production of iron ore raw materials and its transportation during mining and ore processing. Sadarova et al. 25 presented a mathematical model of the production of raw material from a mining area to started point of next technological process. They suggested 2 methods for modeling. The first methods was based on traffic modeling with mathematical equations. The second method based on computer simulation using XtendSim8. The previous transportation models were based on ore reserves and transportation distance, but it did not take into consideration the transportation costs of different locations. Also, the gravity center calculations are not accurate due to uniformity or thickness assumption and method of calculation. The present model will avoid the shortcomings of the previous models to obtain optimum location of processing plant. The current model applied in Aljalamid area of Saudi Arabia, the ore located in 3 locations that are Fish, Southern, and Western. In this case, selection of optimum location of processing plant represents a real challenge. The suggested model studied factors such as number of locations, reserves in each location, transportation costs of 1 ton for 1 unit distance in different locations, and the distance from the gravity center of each location to optimum location of the processing plant. 2. Theoretical consideration. 2.1 General. Choice of optimum location of ore processing factory depends upon the total transportation cost. Transportation cost parameters is dependent mainly upon the reserves of each ore deposit area, the distances of ore transportation from each ore deposit area to the optimum location, and transportation costs per ton in different locations. 2.2 Mathematical Model. The suggested model depends on the minimum sum of transportation cost from ore deposit locations to optimum location of processing plant. Ore deposits scattered into different locations, n. Each location has an ore reserves of chi, which is considered to be concentrated at a defined point that is the center of gravity having coordinates 11, y, zi. The cost of transported 1 ton for 1 kilometer distance from each ore deposit location to optimum location, ci. All of the ore reserves are to be transported to a location where the mineral processing plant is to be construct so that the transportation cost should be minimized. Hence, this issue can be mathematically expressed as in equations from 1 to 6. The suggested model based on the minimum sum of transportation cost of different ore deposits to optimum location of processing plant as shown in equation 1. Where n, number of ore deposit locations. I, to denote the th ore deposit location. Chi, reserves of ore deposit location of location number, I, in, tons. Ci, transportation cost of 1 ton for 1 unit distance for each path or transportation method in, U.S$/ton m. D, distance between different ore locations and processing plant optimum location in, m. X, Y, Z, the coordinates of processing plant optimum location. 11, Y, Zi, the coordinates of the gravity center of different ore deposit locations. The total transportation cost, US dollar, of ore deposit is 2. The distance, d, between 2 points by using its coordinates can be mathematically equals. Hence, S from equation 2 may be mathematically expressed as follows. 3. For this sum to be minimum, the partial differentiation in regards to x, y, and z should equal 0, which means that the following conditions have to be satisfied. Where S, total cost of transportation for all ore deposit locations, US dollar. The partial differentials of equation 3. 2.3 Calculation of ore reserves and center of gravity of ore deposit. The objective of gravity center determination is to accumulate the quantity of ore reserves of each area or location at a point that has coordinates 11, y, zi. Gravity center means an imaginary point in a body of matter where, for convenience in certain calculations, the total weight of the body may be thought to be concentrated 26. The center of gravity of ore deposit can be determined as follows. Firstly, the ore deposit map or area is divided into suitable number of triangles. Each triangle consists of 3 boreholes as shown in figure 1. Secondly, determination of ore reserves and center of gravity of each triangle. Gravity center of a triangle is the intersection point of its medians 27 as shown in figure 2. The center of gravity divides each of the medians in the ratio 2:1, which is to say it is located of the perpendicular distance between each side and the opposing point. Its Cartesian coordinates are the means of the coordinates of the 3 vertices. That is, if the 3 vertices are, and, then the x and y coordinates of the center of gravity can be calculated by equation 7. Thirdly, determination of z coordinate of gravity center of a triangle. Z coordinate of gravity center of a triangle can be determined for the point, which was determined in the second step. Z coordinate of gravity center of the triangle can be calculated by equation 8. 3 Results and discussions. The suggested mathematical model was applied in Aljalamid phosphate ore deposit. In the northern part of Saudi Arabia, the ore is spread on 3 different locations that are Fish Area, Southern Area, and Western Area. 3.1 The center of gravity of ore deposit. Data of boreholes were obtained from Mahran Company for Aljalamid deposit. These data represent 3 different locations. Determination of gravity center coordinates of ore deposit consists of 2 steps as follows. First, calculation of the gravity center of each triangle of ore deposit using equations 7, 8. Second, application of the moment method, equations 9, 10, 11. The ore reserves and gravity center of different locations of Aljalamid phosphate ore deposits are shown in Table 1. 3.2 Optimum processing plant location. The optimum location of processing plant requires the number of ore deposit locations, n, reserves, chi, and center of gravity for each location, 11 YZI. The equations 4, 5 and 6 of model can be used in the form of 12, 13, and 14 as follows. The unknowns in equations 12, 13, and 14 are x, y and z coordinates of the optimum location of the processing plant. These equations represent the mathematical model. Computer program was developed to solve these equations. 3.3 Model validation. Validation step of model is one of main important steps of modeling. Validation based on the values of equations 12, 13, and 14 equals 0 by using the input data of different locations and the calculated result of optimum location. Model validation can be summarized as follows. 1. Specify number of main locations of ore deposit, n. 2. Specify ore reserves of each location chi. 3. Specify gravity center coordinates for each location, 11 Zi. 4. Specify cost of transportation in different locations or paths to optimum location. 5. Input the above data in steps from 1 to 4. 6. Run the developed program to obtain optimum location coordinates of processing plant. 7. Calculate the values of the equations 12, 13 and 14 using the coordinates of optimum location resulted from step 6, and input values of steps from 1 to 4. 8. If the calculated values of equations 12, 13, and 14, in step 7 were 0 or within the permissible errors, it means the model is valid. 9. The above steps were repeated for 10 varied cases with different program inputs, variables, n, q, c, and center of gravity coordinates. Table 2 shows the obtained results for 10 validation cases together with their corresponding errors. As an example, the output result of case number 1 is shown in Figure 4 and Figure 5. Where Figure 4 shows a snapshot of the program with the input variables and Figure 5 shows a snapshot of program final results of the optimum location for case number 1.